It is recording, and I do have audio. Okay. Last week, or last time, which I guess was Wednesday, we finished up chapter 2-2. We looked at the three kinds of graphs: the histogram, the frequency polygon, and the ogive. And we looked at some of the distribution shapes. Remember, we had bell and uniform shape distributions, and we had J and reverse J, right and left skewed, and then we had binomial and U-shaped. Well, we did a couple of exercises where we looked at how you would process the data set, the raw data that you were given to produce these different kinds of graphs. Well, today we're going to look at the different other kinds of graphs. And I'm on page 75 or 2-35, depending on which corner of the page you're reading. First kind of graph we've got is bar graph, which you've seen. I mean, that's basically what we use for a frequency distribution, is a vertical bar graph. Of course, they point out that a bar graph doesn't have to be vertical. It can be, the bars can be oriented horizontally. Depending on how you think it most intuitively represents the data that you're presenting. You will also notice that not every time do the bars touch. But sometimes you'll see space between the bars. Ideally, when you're doing a frequency graph, like we've done like we worked on in the past, where you have boundaries between classes, and the boundaries are adjacent, then it's kind of helpful to make the bars touch, so it kind of makes it sort of intuitive that there's no gap here for stuff to fall between. But especially when you're dealing with nominative or categorical frequencies, that's really not necessarily a rule. The definition there on the bottom of page 75 tells us a bar graph represents the data by using vertical or horizontal bars whose heights or lengths represent the frequency of the data. And they give a couple of examples. Now, are you online with that thing there? See if you can pull up Google and ask them how to pronounce Pareto. Because honestly, I'm not sure how it's pronounced. I call it Pareto or Pareto. 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 Okay. Well, now we know how to pronounce it. Do you want to know what it is? Pareto graph. I'm going to have to get used to saying that. If you take a frequency distribution, specifically a nominative or a categorical frequency distribution, and it kind of has to be one. It can't be a quantitative or ordered, because basically what makes it a Pareto is when you reorder the classes, and you put the classes in order from highest to lowest frequency. So anytime you have a Pareto graph, it's always going to be the bars are going to be like that, going from highest to lowest. And that's what makes it a Pareto. I looked through the book here. Really, that's the only reason for doing it, is if you want to make it, if you want to present the data in order of frequency, in order of descending frequency. That's the only reason to do it, so that you can look and immediately know, okay, well, in this case it was police calls and said, well, juvenile complaints was the most frequent call we got. Yeah. They also have what are called time series graphs. At least that one is kind of more a little bit obvious, at least, as to why you would want to do a time series graph. When you want to show that when you want to show frequency as a divided in where your classes are basically periods of time. If you divide your data up into classes of time periods, then you have a time series graph. Now this is one I bet everybody is familiar with. You've seen these pie charts or pie graphs. Pie graphs are visually intuitive. They make it very obvious very quickly what you're doing, what you're looking at. They do a very good job of giving the viewer, giving the person you're presenting the data to, it gives them a really intuitive, I keep using that word, don't I? There's a reason. It's the whole point of doing graphs, is you want to present the data, but you want to make it meaningful to the person. Okay? That means you want them to have a gut, visceral understanding of what this data means, without having to think it through and analyze it. Exactly. And a pie chart does that very well, as long as you're talking about relative data, because that's what you're doing. You're presenting each piece as it relates to the whole. So it kind of necessarily becomes a percentage or a relative kind of graph. Another format that is often used is called a dot plot. Dot plots. Why would you use a dot plot? Well, honestly, I think originally it was because they were done on computers with dot matrix printers and keyboards, typewriters with keyboards that, how else would you do it? I don't know if it's still true, but in the early versions of spreadsheets with Lotus 1-2-3 and the early versions of Quattro Pro, that was one of the standard ways of presenting a graph. Was you would just load the cell with dots for the relative frequencies, and then the cells just naturally lined up. You're still going to find sometimes that dot plots are handy. They're useful. They're generally easy to, well, not really, can't say they're easy to construct, because now all of the graph, any graph you make is going to be computer generated. So you type the data into your spreadsheet and tell it make a graph, and it makes a graph. But dot plots, what does a dot plot what does that present to you? What does it make you realize, make you just naturally understand that you would have had to have thought about? Well, I think look at let's look at these different approaches. We've got a bar graph. Shows these relative frequencies. Now, we can use the same data to produce a frequency polygon, or a line graph, bar graph, line graph. But both of these make it look like some kind of continuous value. Whereas a dot plot makes it very evident. Well, let me make these big enough to see. Makes it very evident that you're talking about discrete events, discrete items. You know, that these aren't just some or some quantity, some total value of X. They're actually discrete number of quantity of items or data that you have actually counted out. There's a whole nother kind of, I don't want to call it a kind of a dot plot, but I think of it as such, called a scatter plot we're going to get to in a little bit. Now those are extremely helpful. But before we get to there, we're going to have to talk about what's called a stem and leaf plot. And I want to take a couple of minutes to go over these. What is the point of doing a stem and leaf plot? And what is a stem and leaf plot? The principal purpose behind using a stem and leaf plot is you don't just present someone with a visualization of the data, you actually present them with the data, the actual numbers. But you do so in a way that they're organized and structured so as to give you some understanding of the relative abundance, the relative frequencies. Here, let's go work through this example 214 on page 84. We've got this block of 1, 2, 3, 4 times 5 is 20 numbers. And it's the number of cardiograms performed every day for 20 days. And the number of cardiograms that this hospital performed every day. They collected the data over 20 days. Well, to make a stem and leaf plot, the first thing you do is you put the data in order. And that isn't really necessary that you put them in order, but it's helpful, and you'll see why here in just a minute. So we're going to go with our 20 data in order. We've got the lowest number, well, so I'm going to write it from bottom to top, is 02. The next is 13 and 14. Then we've got 20, 23, and 25. 31, 32 4 times. $33 and $36. Then we got 43 and 2 44s. Followed by a 45. And then 51, 52, and 57. Now, each one of these numbers represents a 24-hour period. But we've changed the order of those 24-hour periods so as to put the data in sequence, in order. Now, the way we do it, and you'll notice how already it kind of looks like a little bit like a horizontal bar graph. Well, that's what we're doing. I guess I'm going to switch it over and do it the same way they do it in the book. But what you do in a stem and leaf graph is you take the first digit, and that becomes your stem. So in the first one we have 0, and the second digit becomes the leaf. So we have, on the 0 stem, we have 1 leaf, a 2. On the next stem is 1, and under 1 we have a 3, a leaf of 3, followed by a leaf of 4. On our 2, we have a 0, 3, and 5. 3, we have a 1, a 2, 1, 2, 3 more 2s, a 3 and a 6. Now for 4, we have a 3, 2 4s, and a 5. And under 5, we have a 1, 2, and 7. That is a stem and leaf plot. So we know that on one day we had less than 10. Okay? And that on that one day only we had only 2. We know that on 2 days we had more than 10. We had 13 and 14. And on 3 days we had more than 20. We had 20 on one day, 23 and 25. We know that on 1, 2, 3, 4, 5, 6, 7 days we had more than 30. 31, 4 days of 32, 1 day of 33, and a 36. You see how this works? This is a stem and leaf plot. This is not given, this was not something you construct just so you can make the data intuitive. You construct one of these because you want to make the data intuitive. You want to make it obvious what they're seeing. You want to see the relative frequencies and the distribution of the data, but you also want to be able to analyze the data as well. You want to keep the data intact. Right? That is a stem and leaf plot. Now, there is something you need to I want to point out to you. What if there had been no days where there was more than 40 but less than 50? What if there had been no 40 anythings in the data? Then that's your stem and leaf plot. You still put the stem for 40, for the 40 range, or the 40 class, but you leave you don't put up any leaves. You don't put zeros, because if you put a zero there, that would tell you that on one day you had 40. So you leave it blank, and that tells you that there are no days where you had 40 anything. That you went from 30s straight to 50, that for some reason all right. The next section they talk about are ways to make graphs misleading. And yes, people will do this. So turn in your books to page 86 and 87. Because they've already gone to the trouble of drawing the pictures in the book, so no reason for me to draw them over on the board. Look in figure 220 and 221. And you will see the same exact data presented in both cases. But look at how figure 2-20, the top one, makes it look like there's a whole lot more difference between competitor 1 and competitor 2 and the manufacturer and the main manufacturer. Manufacturer's automobiles that are still on the road is much taller than either of its competitors. But how is that accomplished? How do they make it look like that? Well, look at the vertical axis. Yeah, they've zoomed in on just the tops of the graphs of the bars. But if you look at the horizontal, look at the vertical axis, they start at 95 at the bottom and only go up to 100 at the top. So it only goes from 95 to 100. Okay? If you plot the same data, but start your vertical axis at 0 and go up to 100, then you see, well, wait a minute, there's not really that much difference. After all, we're talking about the difference between 96 and 98. Yeah, it's okay. Now, why might you do this? Why might you use this technique when you're presenting a graph? Well, there could be a perfectly legitimate reason to do this. As he was saying, you might, if you want to focus on this fine detail, then yes, zoom in on it so you get greater difference, and you can look at this fine detail, but make sure that you understand the magnitude of what you're dealing with, that you have zoomed in to see fine detail that you wouldn't otherwise. The other reason you might do this is if you're the manufacturer putting the graph together and you want to make it look like your cars are much, much more reliable than your competitors. So it's a kind of, like I said at the beginning of the semester, there are small lies, there are big lies, and there are statistics. Okay? But at the end of the day, if you put one foot in a bucket of ice water and the other foot in a bucket of boiling water, on average, you will not be comfortable. They do another example here on the next page, page 88, where they show the miles per gallon comparison between 2008, 2009, 2010, and 2011. And on the bottom graph, where they zoom in on just the range where the difference, it looks like that, graphically, visually, it looks like, well, this is a very pronounced difference. Well, when you actually put an actual full scale on the vertical axis, it turns out not really so much. Now here's another trick that people will use. And it's in figure 223 on page 89. Now here, what are they doing? They're taking the data, and there is a truly significant difference between it's the cost in millions of dollars for a 30-second Super Bowl ad, comparing 1967 to 2013. Okay? Well, in 1967, the Super Bowl, they couldn't even fill the stadium. It was like, the stadium was half empty when they played Super Bowl I. Okay? So guess what? They didn't command very much money for their half-hour commercials. In 2013, that was no longer true. Okay? And they command millions of dollars for every half-hour commercial. So, in figure on the left side there, in graph A, using bars, they present that data in one dimension, and you see an accurate representation of the difference between those 2 years. But look how much bigger it looks when they do it in 2 dimensions instead of 1. So in graph B, the diameter of the big circle is still the same height as the bar graph, and the diameter of the little circle is the same height as the bar graph. But because you've made it a 2-dimensional thing now, your eye is going to naturally compare the area of the circle, not just the diameter. And that makes it look like it's a whole lot more pronounced of a difference than it actually is. I honestly can't think of a legitimate reason to do it that way, other than to try and deceive the person that you're presenting the data to. And then they point out this bottom one here. It's not a completely meaningless comparison. It gives you a good visual representation of various differences, relative differences. But since there are no units, not the graphs, the axes are not quantified, there's no units, you're going to be limited at just how much analysis you can actually do from this. Are these graphs zoomed in so all you see is the very tops of the bars? Are they full scale axis? Is it a full scale vertical axis? You don't know. There's simply not that much information presented. That's the end of section 2.3. And in 2.4, we're going to look at paired data and scatter plots. And I really do want y'all to know about these, because these scatter plots are invaluable. And this is something you really do need to know. When do you use them? The example here in the book shows the number of wet bike accidents and the number of wet bike fatalities. Okay? Now, don't quote me on this, but I'm assuming a wet bike is like one of those personal watercrafts, like what do they call them? Wave runners, stuff like that. Yeah, I guess they call them jet skis. I don't. To me, a jet ski, I remember when Kawasaki introduced the first jet ski. And it was one with the handlebars that stood up, and you actually stood up on it. And it was more like surfing than riding a bike. But at any rate, whatever these wet bikes are, whether they're jet skis or wave runners or whatever, you have data on the number of accidents in certain, over the years. And you have every year for a 10-year period. In the first year, there were 376 accidents and 5 fatalities. In the second year, there were 650 accidents and 20 fatalities. In the third year, there were 884 accidents, still only 20 fatalities. How strong is the correlation between the number of fatalities and the number of accidents? I mean, you would expect that it's going to be kind of hard to have more fatalities than you have accidents. So there's got to be some kind of correlation there, but how strong is it? And how much? I mean, because look, it went from 650 to 884. That's what, 25% increase in number of accidents? No increase in fatalities. Well, the way you look for that correlation is with a scatter plot. And you can see this data presented in a scatter plot on the top of page 101 in figure 225. Now, this is that other version of a dot plot kind of graphing, where you don't put bars or anything else. You plot the data as a point, but in this case, you plot it in 2 dimensions, as a 2-dimensional point, or an ordered pair. You do remember from your algebra class, the Cartesian coordinate system, ordered pairs, the x and y coordinate. Well, that's how you do. But instead of drawing bars or anything like that, you just plot the data point in the 2 dimensions and look for a relationship. And you can see in this one, there's a pretty good. I mean, those points kind of line up, look like a pretty good vertically rising line. That there is a pretty good correlation between as the number of accidents go up, so do the number of fatalities. And it looks like a pretty straight line. What's the word for that? Linear relationship, exactly. Turn the page to 102. And there at the top you will see 4 different scatter plots. You see in A, example A, the top left corner, you see a positive linear relationship. If you were plotting that as a function, it would be mx plus b, where m is the slope, in this case a positive number, and b is the offset, or the y-intercept. Now, if you look at the second graph there, the second scatter plot, you see that one has a negative linear relationship. And if you were writing it out as a function, it would be minus mx plus b, because it has a negative linear relationship. How would you describe the relationship in plot C? It is definitely nonlinear. It is not a straight line. What kind of nonlinear? That would be a quadratic relationship. And if you'll think back to your algebra for If it's x cubed, your graph is going to have two humps, two inversion points. If it's x squared, you'll have one inversion point. If it's x to the power of 1, it'll be linear, a straight line up or down. If it's x to the 0, what is that? That's constant. Anything to the power of 0 is 1. So it doesn't change with x. It stays the same. Just off the top of your head, what would you guess would be if you had x to the power of 4? You'd have 3 inversions. X to the power of 5, you would expect 4 of them. Okay? You can also have exponential and logarithmic. All of these are interesting, but that's the powerful one. That's the one that at the end of this semester, we're actually going to take and you will learn to do regressions, where you take scatter plot data and fit the best line you can to it. Something called least squares method. Then, of course, there's the final one here, where there's, it really does look like a scatter plot. It's like someone shot the graph with a shotgun, a bird shot, and you just got points scattered all over the place. So there's no relationship, no discernible relationship in that data. And that, I do believe, is the end of our chapter. And the end of everything that we're going to cover on Exam 1 come Monday. So, we've got another 20 or so minutes. Who has questions from the homework or from the material that we've covered in these 2 chapters?
Is there anything specific that you just absolutely must to know?
I would say everything we've covered in chapters 1 and 2, but I don't want to sound coy because I will tell you this: you can expect the exam problem questions to look like the questions you find in the backs of the chapters. Okay. Obviously, I'm not going to give you a 500 sample data set to work with. It's going to be something you can do in the hour that you have for the exam. But there are a couple of things that I would like y'all to rethink, because I don't remember who, but I know may have been a couple of you. There were a couple of things that seemed like they kind of confused you. The first one that I remember is the difference between dependent and independent variables. Okay? So you're asked about, this is the data set. Which is the dependent variable and which is the independent variable? And it can be confusing because, quite frankly, sometimes it's just an arbitrary choice. But in general, when you're plotting x and y, when you're plotting a function on a Cartesian plane, you're going to write y is equal to some function of x. Right? Well, that means that the value of y depends on the value of x that you plug in. Okay? You cannot plug in, you cannot choose any value of y and come up with an x that will, you can't necessarily pick any value of y and come up with an x that will give you that value. But you can pick any value of x and come up with that value for y. So x is independent. Y is dependent. I don't remember the problem in the homework now, but it was something like the researcher found that people went to McDonald's to eat more as their income increased. Okay? Well, all the problems up until then had been phrased the other way around, saying where it was written out like the researcher found that as the income increased, the frequency of McDonald's visits went up. And that made it, okay, well, this is the independent variable and that's the dependent variable. But when they swapped them around, it looked like it started getting a little confusing. But it's still, as income increased, so did McDonald's visits. This one can be very tricky because there will be times when it is an arbitrary choice. Suppose someone collects a bunch of data, and the data says that they're looking at how restless were the people based on how much coffee they consumed. So they take a bunch of people, they interview them, they find out that they come up with some measure of restlessness, and they establish that point for every person, and then they establish some amount of coffee that person drank. And they find out that as coffee consumption increased, so did restlessness. A nice linear relationship. So from that, can they conclude that the more coffee you drink, the more restless you're going to be? You could, but could you also just as legitimately conclude that the more restless you are, the more coffee you're going to drink? Yeah. See, it becomes a question of correlation versus causality. Okay? You can't really say which one causes the other. Okay? It's possible that if you drink more coffee, it will cause more restlessness. But it's just as possible that the more restless you are, that will cause you to drink more coffee. Because you're looking to soothe your nerves. Okay? In that case, which one is the dependent variable and which one is the independent variable becomes an arbitrary choice. You could just as easily and just as legitimately make coffee the independent variable and restlessness the dependent variable. Okay, it's anytime if all you know is correlation and you do not understand the causality, then it can become kind of arbitrary. So be careful to read the question as how is it phrased to determine which one is increasing and which one is going up as a consequence. And I will try my very best to make sure that we don't put in that no questions show up in there that are ambiguous, that, could be read either way. Or if you find one that is, then make that your answer, that it's ambiguous and could be done either way. Just don't try to use that as a cop-out because again? Oh. It's like every day this week, those fire alarms have gone off, been messing up, and they've had to come out with the workers to fix them. Okay. Yeah, smoke detectors. And it's never the same room. It's one room on Monday, a different room on Tuesday, yet another room on Wednesday, a different one yesterday, and that's right, I forgot about that. All those dead World War II pre-OWs.
That's the only building we have trouble with. They put a second system in, and then it was great for a few months, and now this.
Yeah.
And we're like, how can you guys keep replacing them?
It's all those dead Germans hiding in the tunnels underneath the building. That's it.
Finally get things worked out in the manufacturer, we'll put that thing people, whether it be a baseball bat or...
I was beginning to think that was the reason they won't let us bring guns to school. We fixed that beeper real quick. Worked for my old bathroom scale. So seriously, do either of you have any questions? Anything from the material you want to go back and look at? Anything that you're still not quite clear on or not sure about? C'est bon. Then I will bid you adieu. Have a good weekend, and I will see you on Monday.